Still in section 2.1, this is question 14. Okay, Ryan is riding his skateboard at constant velocity. What do we call that again? Starts with U. Good. For a distance of 40 meters to the north for 9.8 seconds. Okay, so let's draw that in. You guys have this question? Okay, so we have some velocity. We're headed north. Okay, for a distance of 40 meters for 9.8 seconds. Okay. So here we go with this distance 1 of 40 meters and time 1 of 9.8 seconds. Okay. He then travels, so this is V1. He then travels at a constant velocity of 60 meters to the south. Let's call this D2. 60 meters to the south for 15.1 seconds. So T2. Come on, 15.1 seconds. Okay, and here's your V2. So he went south. Okay, calculate speed and velocity. Okay, so for speed, you would need V average. So we have distance divided by time for the total trip. So what is the distance traveled? 100 meters, 40 plus 60. What is the time taken to travel? $100 meters. Oh, you don't have to worry about that. I mean, you can if you want, but get the calculator. Yeah, we can do it. So 100 over 100 meters over 9.8 plus 15.1, 24.9 seconds. So you'll notice when I'm doing my physics, I always get my formula going. And then in my intermediate steps, I don't typically put the units in. It's kind of cumbersome. It takes up your time. And then at the end, I make sure I get my units in there at the end. And I also round appropriately at the end to sig digs. Also, drawing diagrams and establishing variables is key to success. Keeps you organized, keeps you in tune with what the question has set you up with. So 100 divided by 24.9. Okay, I'm getting 4 with a whole bunch of accuracy. Do we need all that accuracy? How many sig digs in this question? Look at my pointer. 2 sig digs, 2 sig digs, 2 sig digs, 3 sig digs. So at most we can have 2. So I'm looking at my decimal 4.016. It's just going to round off 4.0 meters per second. There's my average speed. Now velocity. Velocity, you don't use distance. Correct? You use displacement. Okay? So when you go to sum the two changes in position, you have to keep that in mind. 40 meters north, I'll use a highlighter instead of boxing it. 40 meters north is going to be positive. And 60 meters south is going to be negative because it opposes it. It cancels some of it out. Chris? Okay. I thought you were doing something else. Okay, so we have your 40 meters plus your negative 60 meters. And this is your displacement. This is your change in position. Now, time is not a vector quantity. You can just add these up. it's going to be the same as above. And I've included the units here, but you don't have to until the end. So 40 plus minus 60, you're going minus 20 meters in 24.9 seconds. Negative 20 dividing 24.9 seconds. I have this negative 0.8, and then I'm just going to stop it at there because I'm going to round it off. So in physics, the negative has a meaning. Just direction. Okay? So in this case, with one-dimensional kinematics, it will always either be north-south or east-west. So in this case, negative indicates south. So like the result is you've traveled south at some resulting velocity. Okay, so you can communicate this as negative. I'd be okay with that. You can also communicate it as 0.8 meters per second, comma, south. Okay? Either one of that is fine. Okay? So 15 is similar. I'm going to let you read 15 and try 15, and then I'll put up the solution to 15. Okay, here we go, 15. On a fishing trip, you drive your boat north. So it's often wise to draw a picture. You drive north for 20 kilometers an hour, or at 20 kilometers an hour, for 30 minutes. So right off the hop, you should be understanding that there's an issue here. The issue is in the units. You cannot go with your formula for distance, d1 equal v1 t1, if they don't have corresponding units. Okay? 30 minutes, everybody should know this, that's half an hour. Okay? So if you'd like to show the work on that, you don't have to. We went over this already. You do unit cancellation. So what would you multiply by? What goes in the bottom? Minutes. What goes in the top? Hours. In 1 hour, there's 60 minutes. 30 divided by 60, half. Okay, so this is 0.5 hours. Okay, so 20 kilometers an hour for 0.5 hours, the h's cancel, and the first distance covered is 10 kilometers. You went north for 10 kilometers. Okay, the distance covered is 10. The displacement is 10 kilometers north. Just imagine that in your head. You've gone north for 10 kilometers. Okay? After realizing that you've passed your fishing spot, you turn and you start coming back south. Okay? And travel at 35 kilometers an hour for 10 minutes. So what happened? Are you traveling faster? Maybe you're pissed off that you missed your turn and now you're speeding. Okay? And you only go for 10 minutes. So again, we need to convert those 10 minutes. 10 out of 60, we're getting like this 0.16 repeat, right? Now, when you go to do your calculations, you have to be so careful. You have to have accuracy and precision, right? So please, let me show you. Precision is key. You cannot round in between. Come on, calculator. If I go like something simple like this and end up with something like this, okay, if I want to use this in my next calculation, I can press times whatever it's going to be. Okay, I can also do this. Store, do you see that? Store, and then I can pick a variable. That's an option. Now, anytime I want that decimal, I can just use alpha A. Okay, that's an option. If you have the nice calculator with the silver, you can actually scroll up, hit enter, copy, paste to the next. That's the best way. By just going up and hitting enter on it. Okay, so you absolutely must use You absolutely must not round in between. You round only at the end. Is that clear? Do you round in between? No. Okay, so let's figure out the second distance covered, d2. The second distance covered will be v2, t2. We traveled at 35 kilometers per hour for this 0.16 repeater of an hour. Okay? So 35 times 1/6, we got 5.83 repeater. And this is kilometers south. So what's happened? What's your net result? If you spend $10 and then earn $20, what happens? There's a net result, right? Same in physics, okay? If you travel north for 10 and then south for 5.83, what's the result? Your net is north, right? So that's why I drew my north arrow larger than my south arrow. And if I was to put those together like this, here's my north, here's my south, what's the result? This is the result, okay? This is where I ended up from my original position, which was here, okay? I would use this value in purple for my velocity on average, and I would have to use both the black arrows for my average speed, because speed depends on distance and the velocity depends on displacement. Okay, so now you can just use what we did in 14 here to cover the rest of this. Okay? Two-step problem here. All right? Okay, so let's just do the speed calculation. And people were using S. Do not do that. Do not use S. Okay, use V for speed and V with the line on top for velocity. Okay? So speed will be d over t, our 10 plus 5.83, all over the total time, which is 40 minutes. Okay, so 40 out of 60. That will be our V average. Okay, so this will work out plus 10 divided by 4/6. 23.75 kilometers per hour. Okay. Why do I have 40 out of 60 in the denominator for time? What's the total time? First trip was 30 minutes. Second trip was 10 minutes. 30 plus 10, 40 minutes. But out of 60 because we need it to be in hours. Okay. Now we can jump into the velocity calculation. Okay, let's do the velocity now. Speed and now velocity. Okay, and it's all about this average velocity. So now we'll use displacement over time. The time will be the same. It's still 40 out of 60. Okay, but now the displacement. So when you go to do the calculation, just like we did above here, we don't just add it up like this. We have to add, but being direction aware. So a positive 10 for north plus a negative 5.83 for south. Okay? So 10 minus. And on my calculator, I just go back up to that 5.83, highlight it, so I can get my complete accuracy. And now I can divide that by 4/6 in a bracket. Okay, and I get 6.25 kilometer per hour. And because it's a velocity, I need to be direction aware. What happened with my calculator? Did it spit out positive or did it spit out negative? It spit out positive. So I know that the net result, and even from my picture, I know that the net result is north of my displacement, or north of my original position. Okay, first, before we get into the graphs, let's look at 17. Speed and velocity are always relative to a reference point. Okay? Often that reference point is the ground. So Jessica, riding on a bus, traveling at 30 kilometers an hour, says, under the conditions listed below, determine her speed relative to the bus and relative to the ground. If her walking speed is 5 kilometers per hour, complete the chart. Okay. When you're driving in a car, do you have the same speed as the car? Yeah. You take on the car's speed, right? Now, in a bus, you can get up and move around. So, if you're sitting in the seat, you have the bus's speed relative to the ground. Now, if you get up on that bus and start moving, you have the bus's speed plus your speed. Okay, so say I was going 30 kilometers an hour to the right. Let's go this way on the bus. So I'm sitting on my chair. I'm going 30 kilometers with the bus. I get up and start walking at 2 kilometers an hour on the bus. How fast am I going relative to the ground? Yeah, 32. It's the bus's speed plus your speed. Okay? Now this one's weird. Sitting out there 30 kilometers an hour. You get up, bus is going that way, and I start going this way. 2 kilometers an hour. How fast am I going? 28. I'm going 2. I'm going 2 to the left, to this way, to your right. I'm going 2 to your right. The bus is going 30 to the left. So here's the bus. I'm going this way at 2. Bus is going 30. So what am I actually doing? Relative to the ground. Relative to the ground, I'm an observer out there watching me do this. What does the observer see me do? I'm going that way to the observer. Even though I think I'm walking this way. Relative to the bus. This is like relativity. Okay? In this world of the bus, I have my own like view of what's happening. But to an observer outside the bus, he sees something different. Okay? Yeah. Okay, let's do it again. Bus is going this way, 30 kilometers an hour. I get up and start going 2 kilometers this way. To an observer outside, he sees me actually going that way, my opposite way that I'm walking. It's weird. But on the bus, I think I'm going like, relative to the bus, I'm going 2 kilometers an hour this way. But to the ground, outside the observer, I'm actually going 28 that way. So fill in this chart. Okay, fill in the chart. Careful. It's all about the observer. Okay. So sitting down, you have the same speed as the bus. You are the bus. You become the bus, right? And this is relative to the ground. This is to an observer outside the bus. He sees you going 30 kilometers an hour, whatever direction that is. Okay? So, relative to the bus, you're not doing anything. Now, to the observer inside the bus, a guy looks over at you, you look over at him, you're not moving, right? You're not moving. Right? That's logic, that's common sense. You're not moving. But to an observer who's watching the bus, you are moving. Okay, when you're walking to the front, you'd be walking in the same direction as the bus. So this is like the principle of superposition. It combines. 30 plus 5 is 35. But relative to the bus, you're actually only traveling 5. Good. Now walking to the back, you'd be going 25 because it opposes. Principle of superposition. Either you combine and grow or you combine and shrink because it's in the opposite direction. And this would actually be negative 5 relative to the bus. Are they asking for, yeah, and its speed. So the velocity would be negative 5. but the speed would just be 5. I wish this said velocity, but whatever. Yeah, technically it should just be 5 for speed, but you're going the opposite direction, so it should be negative. Like you don't use speed in physics. It's always velocity.
Are there going to be questions where you use an observer that's in another car traveling faster or something as to what it would look like?
Like if one car is traveling 50 and another car is traveling 60?
Yeah, like if an observer, say, in another car traveling 60 sees you traveling at what relative to...
Yeah. Yeah, and you would just be combining with adding and subtracting. Yeah. Okay, let's get into the graph stuff. So again, with those previous 16 questions, the first 13 are like a physics 10 review, science 10 review. So I assigned it for homework. If you have questions with that, you can stick around after school. I got the solutions manual up here. You can take pictures of it. Let's move into some of this graph stuff. So we got displacement versus time for an object in uniform motion. This uniform motion tells us that it will be curved or linear. Okay, linear. So we need to draw some linear curves. Okay, so, or some linear graphs, pardon me. And if it's moving in a positive direction, will the slope be positive? Yes. And if it's moving in a negative direction, it would just be negative. Just make sure you draw straight lines. Don't do what I just did. Draw a straight line. Use a straight edge. All right. Okay. Now, you probably took this in Math 10. There's a graphing unit in that. So let's take a look. Where is this person stationary? Because the line is good, horizontal. Yeah, flat or horizontal. This is called constant. Constant speed. Because the position versus time is not changing. Oops, what am I doing? Pardon me. I highlighted the wrong thing, didn't I? I don't want to confuse you guys. Stationary. Here. Because your position is not changing, you are not moving. Is E flat? Okay, if you look at this graph, your position is not changing as time moves on, so you can't be moving. Is E flat? Okay, highlight E as well. Okay, and then what's the difference between walking and running? What's the only difference? Okay, so walking is slower, running is faster. What property of a linear graph are we looking for? Good, but what part of the slope? The steepness. So which parts are steeper? So C, I'm assuming you'd be running because it's steeper. Now let's look at C and D. What's different between C and D? One has a negative slope and the other has a positive slope. So what's happening in C and D? Are you running away from your start point or towards your start point? What's happening? For C, and away from your start point for D. Good. Number 20. The position of a car over time was recorded and graphed. So how to find velocity off of a position time graph? It's in the notes yesterday. How to find the velocity off a position time graph? Find the slope. Good. Now, how to find the slope of a line of best fit. We did this last week or early this week. You have to find 2 points off the line. We need to find 2 points that will work well. Oh, I see one. Here's a good one. Why is that a good one? It's like right on the grid, right? Is there another good one anywhere? On 10? 10 would be like just underneath that line, hey? Just under 11. So what you can do is pick some points. This one looks like a hair underneath.
Teachers, please excuse this interruption. Just before we get to home time here, just want to remind any students that still have not had their timetables corrected. Today is the last day for you to come down. The student services team will be working after school to address any of those. So again, students, this is your last opportunity to come down and have those done. So that'll start after dismissal, not before dismissal. So again, if you have changes that you are required to schedule, please come down to the office after dismissal. And as well as Aaron Bird, if you're in the office or in the school, can you come down to the office, please? Thank you guys and have a great weekend.
All right. So the reason I chose to put 10.9 there is just because it's like a hair under 11. So I went 1 decimal place. It might be 10.8. It might be 10.95. Again, there's going to be some error in everybody's calculation. There's some error in your accuracy. Okay, so slope. The slope formula, of course, m equals y2 minus y1 over x2 minus x1. M is not the mass like in physics. It's just weird that m is also like a unit for meters and stuff. So be context aware. This m is the slope formula from math. It's not mass and it's not meters. So anyways. So again, slope formula, we've already showed this, but 10.9 and 7, that's going to go up top. Start with the second point always, 10.9 and 7. And then in the bottom, we'll use 10 and 5. 10 minus 5. So 10.9 minus 7, and dividing that by 5, I got 0.78. And again, there's going to be some error in everybody's calculation. So you notice their answer book is 0.77, but they have the approximation symbol, so they're not saying that this is absolute 0.77. But notice the direction. They've included west. Why is it west? It says west, and the slope is positive. Right? So the position of a car over time as it travels west. Okay, if this was going down to the right, if the slope was negative, you'd be going east. Good? Okay, so don't forget you need to indicate direction because it's asking for the velocity. Okay? Little details in physics. Sometimes they can make us or they break us. The details. Okay, so for number 21, it's just a bunch of slope calculations, so I'll let you guys do that for homework. Same with 22 and 23. 22 and 23, if you're stuck, you can visit the appendix at the back of the book for some help. So please practice your slope calculations. Somebody at the door.
Hi, so we were doing the welcome week for the students, and now we got t-shirts for the teachers.
Cool. Is there extra large? I'm a big guy.
Pretty sure it is. If it's not, then
What's the size on that? Look, go to the. See, look, it even has my name on it.
no, it's for Hammer.
Oh, that one flipped off.
Yeah.
You're a good man. Thank you.
You're welcome.
Okay, so then it flips into 24. Please take a look at 24. 24 is also in the appendix, so if you get stuck. Okay, let's take a look at 24. I want you guys to finish this section off for homework tonight, so, or for the weekend. Because then we can start acceleration next block on Monday. Okay, let's look at 24. A boy goes for a walk from left to right. Is that one-dimensional? Yeah, so you just basically imagine a point moving left and right. That's all it can do. Okay? The distance is marked along the ground in meters and the stopwatch values are in seconds. Note the direction he is facing for an indication of which way he is moving. Motion may be represented using either charts or graphs. Complete the chart of the motion, assuming it is always uniform. So you'll always have the same speed. Okay, so part A, how far has he traveled? 0 meters. And how long did it take him to do that? 0 seconds. Part B. Okay. How far has he gone in part B? How many ticks? In 10 seconds, he's gone 30 meters. Okay. So we're going to skip the one because he hasn't technically gotten here yet, right? He's traveling this way, right? So now at part C, it's been 20 seconds, right? You can see the clock. And how far has he gone? 60, 70, 80? 80 meters. Hold on. And then what happens yeah, good. Is that what you're saying, Sean? Good. So at 30 seconds, he's in the same position at C here. So yes, good observation. You repeat 80. So he's been stationary for 10 seconds. Agreed? Okay, and then at position D, we just did that one, so now we're at E, so he keeps going a bit. This is at 40 seconds. And he's at 120. And then looks like he turns around. But again, this is all on one line. So he just basically turns around in the spot and goes back along the line and ends up at F, which is, oh, what is this? 55? Let's do it. 55. And his position now, careful. Where's 0? Here's 0. So position is back at 50. It's not distance covered. If distance, yeah, it's position. Look at the title. Yeah, position. Okay? So what this will allow you to do is create a position time graph. Okay? This is data, right, from an experiment. You're going to use points and circles, right? Remember? Okay. (25) also in the appendix, okay? You're going to look at the description and you are going to attempt a sketch, okay? Let's do B together. A dog sits for a while, 10 meters to the north of his house. He then runs at a constant velocity to the south until he gets home. So what does this dog sits? No, you're just sketching a graph. He sits for 10 meters north of his house. Good. He's just chilling. His position does not change over time. And then, maybe mommy calls him. Time for food, Sparky. And then he's like, running home. And he's going south. Okay, so do we go up or do we go, or pardon me, do we have a positive slope or a negative slope? And how far do I go till? Because he goes home? Assuming home is the original place. Okay. Think you guys could handle that question? Finish that one off. Let's flip. 26 is similar. Check the appendix if you're having issues, okay? Now we'll go to 27. And 27, I'll think we'll stop there because these are VT graphs. Did I show you VT graphs yet in the notes? Only position time, right? Okay, so let's stop here. Okay, so let's stop here. Up to 26 in homework, okay? Everybody get that done, up to 26. And if you've just joined us, you have all those quizzes you need to accomplish.